Hey everyone. So today is lesson 2 of quadratics, and we're kind of easing you into quadratics since it's our first unit. We kind of want to review some things, make sure you are comfortable with some things from grade 10. For some of you, maybe you didn't have grade 10 in the last semester, and so you're looking at almost a year since you thought about math. So that's why we're kind of easing you into this. Yesterday there was no video because there was also no PowerPoint note. It was a unit opener, but we talked about how to graph things from a table, how to look at the general picture of that, what the difference between continuous data and discrete data is, how to find a y if you're given an x, and how to find an x if you're given a y, all of that sort of stuff. All of that was covered in 10C, so I'm hoping that it was comfortable with you. But as always, if it wasn't, please just come chat with me, okay? Or drop me an email. I want to make sure you're comfortable with everything that we're doing. So that's a good segue into today's lesson, speaking about comfortability. Today we're going to spend a little bit of time reviewing factoring. Now, factoring is probably the absolute most important thing we taught you in 10C. Okay, it's so important, and one of the reasons it's so important, in 20-1, I'm going to actually say probably 75% of this course is factoring. It's just not the question anymore. It's a means to get to whatever answer you're looking for. Okay, so whereas in grade 10, you had to factor because that's what the question was asking you to do. Now the question is going to ask you to do something that factoring is a tool for you to get to the solution. Okay, so why don't we take a little bit of time just to review some of the main types of factoring questions that we see. Okay, all right, so sorry, my slide was not advancing there. Okay, so we'll be using factoring in almost every unit for the entire course. I'm not being dramatic there. Like literally every unit we do is going to involve factoring. It's going to be your most favorite thing. The methods of factoring that we learned in 10C are extremely useful in determining the x-intercepts of polynomial functions. Now we're going to talk more about that in detail later. Later, we will learn other applications of factoring polynomials. Okay, so we're going to take a look at some factoring strategies. The first strategy we always look for when we're trying to factor is creating a greatest common factor. Now, some of you may be watching this and you'd be like, I don't even know what factoring is anymore. Well, let's just stop there for a second. When we factor something, we essentially create a multiplication sentence, okay? If you think about the number 30 for a second, you can say that 30 is 5 times 6, okay? And so we say that 5 is a factor of 30 and 6 is a factor of 30. And the reason we say that is because both 5 and 6 will create a multiplication sentence that will get us back to 30, okay? So factoring is breaking a larger number into smaller numbers that get multiplied together. Okay, now the reason I'm saying that is because when it gets messy with polynomials like you're looking at here, factoring is still about creating that multiplication sentence. So the very first thing you do is you ask yourself, is there any greatest common factor? Is there something in both of these numbers that I could actually take out, put in the front, and that would create my multiplication sentence? So when you're looking at 5x squared y, and you're looking at 25x cubed y to the 4, just deal with each kind of piece first. Between 5 and 25, the greatest common factor there is 5. So I know for sure I'm going to be able to take out a 5. Okay, then I'm looking at, I'm just going to switch colors here to make this a little easier, x squared and x cubed. Well, what's common to both of those piles? X squared is common to both of those piles. So that means I can actually take out an x squared. Okay, then I'm going to take a look at the y's, and I've got a y here, and I've got a y to the 4 here. So that's like there's one y in this pile, and there's 4 y's all being multiplied together in the other pile. Okay, so what's common to both of those piles? Well, there's a y common to both of those piles. Okay, so my greatest common factor is 5x squared y. Now, You don't divide that out, you factor it out. And what that means is that's going to come to the front of my binomial. And I'm going to open up a multiplication. I'm going to open up a bracket so that I create that multiplication sentence. And inside that bracket, I put what's left of those two terms when I divide them by 5x squared y. Now, very common mistake. Well, let's look at that first term for a second. We say, oh, okay, I'm taking out 5x squared y, so I'm left with nothing. That is not true. Everybody hear me? Not true. 10 divided by 10 is 1. 18 divided by 18 is 1. 18 billion divided by 18 billion is 1. Anytime you're taking a number and you're dividing it by the same thing, you're going to get 1. Okay, so 5x squared y divided by 5x squared y is going to give you 1. So the first term inside that bracket will be 1. Okay? Okay, so I take out my 5x and then I state what's left. Sorry, 5x squared y. And I'm left with 1 minus, and then 25x cubed y to the 4 divided by 5x squared y. 25 divided by 5 gives me that 5. X to the 3 divided by x to the 2 gives me, oh, sorry, there's a mistake there. That should be x. Let's just add that in. I'll fix that before I PDF your PowerPoint for you, but 5x and then y to the 4 divided by y gives me y to the 3. Okay, so that should say 1 minus 5x y to the 3, and then that's in brackets, and it's being multiplied by my greatest common factor, which is 5x squared y. Okay, everybody cool? First factoring question. We're going to be factoring machines this year, and we're going to love factoring. Okay, all right, awesome. Next up, what if I had trinomials? Now, I have this set up with 2 different types of trinomials, and depending on who taught you 10C, you may have heard different words. Like, you may have heard that this is called a simple trinomial and this is called a complex trinomial, okay? I don't really care about those words. I don't need you to know them. What I often say with my 10Cs is this has a shortcut involved, this guy here. And the reason it has a shortcut involved is because there's no coefficient on the x squared. Now that's not entirely true. The coefficient is 1, but we're just not writing 1 there. Okay, so there's a coefficient different than 1 on that front term. Now, shortcuts are great if you know the shortcut and you use the shortcut in the right spot, okay? If you are a type of person who might mix up when you can use a shortcut and when you can't use a shortcut, I would just stick to one method of factoring and just do that method of factoring all the time. So the method I'm going to show you for both of these, actually, just to show you that it works either way, is decomposition. Decomposition refers to breaking down the middle term into 2 other terms so that you get 4 terms here instead of 3 terms. And once you have the 4 terms, you factor the front 2, you factor the back 2, and you end up with a greatest common factor that's a binomial that you can pull out. Okay, so I'll show you all of that as we go here. So the first thing we're looking to do is we always are looking to multiply the number here with the number here. So we're looking for 2 numbers that would multiply together to give you -6 and add together to give you -5. Okay, and so we go through our factors of 6. I can do 1 times 6, or I could do 2 times 3. If I need to multiply 2 numbers together and my answer has to be negative, one of those numbers has to be negative. Okay, so if I want to add them together and get a negative number, that tells me the larger number has to be negative. So I know right now that the negative is going to go there. So I add these guys together and see which pair is going to be friendly for me. Which pair is going to give me -5? Well, it's this guy right here. 1 plus -6 will give me -5, and 1 times -6 will give me -6. So those are my friendly numbers that I'm going to break the -5x down into. That's why this is called decomposition. Okay, so I break the -5x into x and -6x. Okay, now that I have that set up, I'm going to factor the front 2 and factor the back 2. Okay, so I'm looking to take the greatest common factor out of both of these guys. So what can I take out of x squared and -6x? I can just take out an x. Then on the other guy, there's actually nothing I can take out, but if I'm doing this process, I have to take out something. So I take out a 1. Okay, so I take out an x from the first two, and I take out a 1 from the second two. When I take out the x, it leaves me with x minus 6. And then when I take out the 1, I'm still left with x minus 6. But now my heart goes pitter-patter because I have a factor that's common in both of these terms. That x minus 6 is common for both terms now. And because that's now a greatest common factor, I can pull it to the front. So I'm actually left with x minus 6 times x plus 1. Now I have a binomial times a binomial. Okay, remember the whole purpose of factoring was we wanted to create a multiplication sentence. I now have a multiplication sentence. I know that x squared minus 5x minus 6 is the same as x minus 6 times x plus 1. Okay, now I said that this was, I could use a shortcut here. You don't have to go through the process of decomposition when the number in front, the coefficient in front here is just a 1. What I want you to notice is those friendly numbers were -6 and 1, and you actually see them appear right in the answer, -6 and 1. So if you are comfortable with that and you like using that shortcut, by all means, go ahead and use that shortcut, okay? I wanted to show you the process of decomposition though, just in case shortcuts kind of mess you up. And in the second example, over to your right there, you can't use the shortcut because now there's a 2 in front, okay? So no shortcut is available to us when there is a coefficient in front. So now I'm looking for two numbers that multiply together to give me -10 and add together to give me -3. So I'm thinking about my factors of 10. I know I can go 1 and 10. I know I can go 2 and 5, and that's it for 10. I know I have to add together to get a negative number, so that means my larger number should be negative. Now I look at these pairs and I say, which is my friendly pair? Which of these pairs is going to add together to give me -3? And the answer to that, of course, is the 2 and the -5. So I'll break this -3 into 2x and -5x. It doesn't matter which one you put first, but that's why we call this decomposition. Decompose means you're breaking something down, okay? So I'll break that down. And now I'm looking at the front two, and I'm looking at the back two, and I'm gonna try and take out the greatest common factor. So what can I take out of a 2x squared and a 2x? I can take out a 2x. Now again, be careful because that's this guy right here. When you take that out, what are you left with? Any number divided by itself is, everybody's yelling, 1. Good. Okay, so I take out the 2x and I'm left with x plus 1. And then I take out a -5 on the back two. And that leaves me also with x plus 1. My heart goes pitter-patter because I have the same thing in the brackets. That means x plus 1 is now a common factor to those two terms. I can pull out the x plus 1, and I'm left with it being multiplied by 2x minus 5. Okay, so x plus 1 times 2x minus 5 is my multiplication sentence now, broken it down into those two factors. Okay, everybody happy? Everybody loving factoring? Remember, if you missed something on this video, the beauty of videos is you can shut me up at any time, you can rewind me, you can pause me. Make sure you're using this to the best, the best resource that you can, okay? Go through things a couple of times if you're confused. Okay, binomials. When we deal with binomials just means we have two terms. In factoring, the biggest thing we're looking for here is something called a difference of squares. A difference of squares is when you have a perfect square minus a perfect square. Now, what I mean by the perfect square is you know what the square root is, okay? X squared, you see this guy right in the front here, x squared is a perfect square because I know its square root. Its square root is x. 16 is a perfect square because I know its square root. Its square root is 4, okay? So with a difference of squares, algebraically, we often say a squared minus b squared. So remember, the word difference here actually does mean subtraction. It doesn't work if it's a squared plus b squared. Okay, it has to be a squared minus b squared. But what that will do is it will factor into two binomials multiplied together, where the first term is the square root of the first guy, so the square root of a squared. And the second term is the square root of the second time, so the square root of b squared. And then one of them gets added, and one of them gets subtracted. If I was to multiply all that together, I would be right back to there, okay? So what's the square root of x squared? It's x. What's the square root of 16? It's 4. So this guy is going to factor into x plus 4 and x minus 4. Okay, now on the second guy, 8d squared minus 32, you may look at that and say, Hill, you're crazy. There is no perfect square there. You're sort of right, there is no perfect square there. But the first step in any factoring question is to always look for that greatest common factor. Is there a greatest common factor between 8d squared and negative 32? Yes, there is. I can actually take out an 8. Now look what happens when I take out that 8. If I take out that 8, I've got d squared minus 4 left. Well, d squared minus 4, that is a perfect, that's a perfect square minus a perfect square. So that is a difference of squares, okay? So the square root of d squared is d, and the square root of 4 is 2. So that now is going to break down into d plus 2 and d minus 2. Be careful with that 8. That 8 is now along for the ride. He has to stay in the front at all times. Don't drop him, okay? So my final answer there is going to be 8 times d plus 2 times d minus 2, okay? All right, then we're going to look at special polynomials, special like my mama told me I was. The first guy here is x squared minus 2xy plus y squared. Now, what's special about this guy is I haven't given you ones where there's squares on the other end too. This is still a friendly trinomial. Now, when I say friendly trinomial, I mean it's something that I can use the process of decomposition with. Doesn't matter what the exponent here is, as long as half of that is represented here. And it's the same thing on the other side. It doesn't matter if there's an exponent here, as long as half of that is represented here. So this is still a nice friendly trinomial. I am looking for two numbers that multiply together to give me 1, because this is 1 times 1. So I want to multiply together to give me 1, and I want to add together to give me negative 2. Those two numbers would be negative 1 and negative 1. If I add negative 1 and negative 1 together, I would get negative 2. But if I multiply negative 1 by negative 1, I get positive 1. Okay, so I'm going to break this term down. Remember now, that term is xy. So when I break it down, both of my terms have to have the xy in them. So it'll be negative xy and negative xy when I break it down. So that's going to look like this. Okay, and now I do the same thing. I'm left with the 4 terms, so I factor the front 2, I factor the back 2, and I see if I have a common factor. And I should have a common factor because that was the whole purpose of what I was doing, right? If you don't get a common factor here, something went wrong. You either didn't choose friendly numbers or you made a mathematical error along the way. So x squared and minus xy, I can take out the x. And then over here, I can take out a negative y. Notice that the front dude, sorry, I should just show you what I'm doing here. In the back 2, if I factor out the back 2, the front dude is negative. If the front dude is negative, you're always factoring out a negative. And remember that when you factor out the negative, that's actually going to switch signs on you for the rest of the terms, okay? So just be careful of that guy. Okay, so I factor out the x and I'm left with x minus y. I factor out the negative y and I'm left with x minus y. My heart goes pitter patter because I have the same thing in the brackets. That's common. That can be pulled. So I have x minus y, and I'm left with x minus y. Now, this is also exciting because I'm left with the same thing. I have a binomial multiplied by itself. So the simpler way of writing this would be x minus y all squared. I don't need to write it twice, okay? Now, this is a special polynomial. It's called a perfect square trinomial because this trinomial breaks down into a binomial that gets multiplied by itself, okay? A binomial that gets multiplied by itself. Okay, now this one also you would have done last year. This looks confusing, but what I want you to see is this is 2 times something squared minus 3 times something, but that something is the same. So often when we have questions like this, we do a quick little substitution so it doesn't look as confusing. And substitutions are great as long as you communicate in math that you're going to perform a substitution, okay? So we would be looking at this as our first statement. Let x equal a plus 2. That means every time I see an a plus 2, I'm going to change it to say x, okay? Now that would be written as 2x squared minus 3x minus 5. I just substituted the a plus 2 for x. Okay, so now I'm going to try and decompose that. So I'm looking for two numbers that multiply together to give me negative 10. and add together to give me -3. Okay, those two numbers were -5 and 2, so I broke my -3x into 2x and -5x. I'm going to factor the front 2, I'm going to factor the back 2, pull a 2x out of the front 2, and I'm left with x plus 1. Pull a -5 out of the back 2, and I'm left with x plus 1. So now I see that that x plus 1 is common. I'm going to pull the x plus 1, and I'll be left with x plus 1 multiplied by 2x minus 5. Now, this was a beautiful factoring question, and everybody's feeling really good. And here's the problem with substitutions like this. Don't stop. Lots of people look at this, and it looks like a nice, pretty answer. So they're like, yay, I'm done. No, you're not, because x was never there in the first place, okay? X is actually a plus 2. So we kind of played a little game of denial up here, and we said, okay, let's just forget about the a plus 2 because that looks confusing. And we switched it to x, and we got down to here. Playing the denial game is totally okay to deal with a math question as long as you face reality at the end. We are now at the end, and we have to face reality. X is not x. X is a plus 2. So I have to substitute it back, okay? So wherever I had x, that's really a plus 2. So this said x plus 1. Now I have it saying, sorry, I was just trying to get ink on. Now I have it saying a plus 2 plus 1. This said 2 times x minus 5. So this is now 2 times a plus 2 minus 5. Okay, you follow me? Okay, so now this is better, but I can simplify that, right? 2 plus 1 is 3. So I'll call that guy a plus 3. And then I'd have to distribute this guy. So that's 2a plus 4. And then I'd have 4 minus 5 there. So that's going to end up being 2a minus 1. Okay, so my simplified version of that would be a plus 3 times 2a minus 1. Okay. Oh, sorry, let me take that ink off. Okay, some basic function terminology. So you did last in 10C, we had the whole unit on relations and functions. So just a quick little review of some things. You should pause me when you see fill in the blanks like this and see if you can figure out the words themselves, okay, before me. Okay, anytime you can figure out the answer before I tell you the answer, it's a good day for you. So do that as much as possible. A relation is a rule that associates the elements of one set with the elements of another set. Relations can be represented by, okay, so here's the main ones. Last year I would have given you actually 7, but these are kind of the main ones. Words, blank pairs, that would be ordered pairs. Table of, you're all yelling value to me. Something else or equations. The other common one that we would use is a graph, okay? So graphs or equations. Now, a function, super, super important, this word. A function is a relation, but it's a special type of relation, okay? Kind of just like a square is a special type of a rectangle. It fits a more specific definition. A function is a relation in which every valid input, and inputs are your x values, there is only one possible output. Outputs are your y values. The vertical line test is an easy way to determine if a relation is a function or not. Now, what the vertical line test does, just as a quick review, is, where's my black marker? There it is. So let's say I had, I'm going to try and draw this nice and big here so you can see it. Let's say I had a graph that looked like that, okay? Now, you've never seen a graph that looked like that, and that's totally fine. But what the vertical line test does is we say, hey, just start drawing vertical lines, okay? And yellow, you can't see at all on this video, so let's switch to green. Let's just start drawing vertical lines. Can you see that? Yeah, okay. What I want you to notice is that vertical line only hits once. Here, here, no matter where I draw that vertical line, it only hits once. That's telling me that this is a function, okay? If at any time, let's say I had something that looked like that up there, if I tried the vertical line test on that guy, uh-oh, it hits twice. If at any time it hits twice, it's no longer a function. It's still a relation. All of these are relations, right? But it's not a function anymore. In order to call it a function, there has to be only one y for every single x, okay? Okay, so the vertical line test is an easy way to determine if a relation is a function. If a vertical line can be drawn intersecting the graph only once, then the graph is a function. If not, all we can do is call that graph a relation, okay? Now, function notation. So we introduced function notation last year to you, and that's this f of x. Now, when we have f of x, we say f at x, or sometimes we say f of x. What we're referring to there, we would have talked last year about the fact that that's a replacement for y, okay? So for the function f, it refers to the value of the output of the function at the input value of x. So let's say I gave you, I don't know, let's say I said f of x equals 3x plus 5, okay? F of x is 3x plus 5. So this is the same as saying y equals 3x plus 5, but we've replaced my y with f of x. The reason I've done that is because now I can look at this function for different values of x. Let's say I did f of 2. Well, what I'm doing there is I've replaced my x with 2. So we're saying there, I want to know the value of this function when f is 2. Okay, so we would keep this as f of 2, but we plug in 2 for x. So 3 times 2 is 6, 6 plus 5 is 11. So f of 2 is 11. The reason we like function notation, it tells us our input and our output at the same time. When the input is 2, the output is 11, okay? All right, so domain is the set of all independent variables. Again, the independent variables are the x values. And then the range is a set of all dependent variables, which would be the y value. So when you're reading domain and range, domain is read from left to right, and you're looking at what x can be, and range is from bottom to top. Your eyes would scan from the bottom to the top, and you're looking at all the things that y can be, okay? All right, also we want to talk about intercepts. Horizontal intercept, also known as the x-intercept, okay? It's the point where a graph intersects the x-axis. Now, when I intersect the x-axis, no matter where I am on the x-axis, just going to give you a quick little visual here. No matter where I am on the x-axis, let's say I was here, that point might be 1, 0, okay? Or let's say I was here, that point might be negative 3, 0. Or let's say I was over here, that point might be 5, 0, okay? The point I'm trying to make, the y value is always 0, because if I'm sitting on the x-axis, I haven't gone up and I haven't gone down. So my y value is 0. Anytime I'm on the x-axis then, the point will be listed as x, whatever the x value is, comma 0. If I ask you for the x-intercept, that word intercept means it's a coordinate point. So don't ever answer like that. That is not cool, okay? You have to write it as a coordinate point. So you'd have to write it as bracket, whatever the x value is, comma 0, okay? Okay, so same kind of lecture on the y-intercept as well. The vertical intercept or the y-intercept is the point which the graph intersects the y-axis. Sorry, I don't have my arrow. Okay, y-intercepts also would be written in a coordinate pair form, but now if I'm on the y-axis, it's actually x that's 0. So they'd be written as 0, comma, whatever the y value is, okay? Awesome, okay, good job, guys. Now, we're gonna determine the domain and range of this graph and then whether it is a relation or a function. So, a couple of things I want you to notice. I want you to notice that this graph spills off of the window that we gave you, okay? Anytime you have a computer-generated graph and it spills off the window like that, you can assume that that goes on forever. You don't need to see arrows there, okay? That's just gonna go on forever and ever and ever like this. Now, when you are drawing graphs, you do have to put arrows there, okay? But Alberta Ed has said for computer-generated graphs, if you see it spilling off your page, then you can assume that it goes on forever. Okay, so when I look at my x values, what can my x values be? Well, if this is gonna go like this all the time, I'm heading to the left forever, and I'm heading to the right forever, which means x can be anything I want it to be, okay? So we say, when x is anything we want it to be, we say x is a member of the reals, okay? And I'll write that up there in 1 sec. I just want to talk about y at the same time. Now, y can't be anything because I see an absolute bottom here to this graph. This graph will not go below -3, So for the range, I have to say y has to be values that are greater than -3 because nothing exists down here and nothing's ever going to exist down there. Okay, so my domain is listed as x is a member of the reals, and the range is listed as y is greater than or equal to -3 and y is a member of the reals. You need to be very, very specific in how you write domain and range. Okay, this is called set builder notation. If you forget any of these pieces, it's not considered completely correct. So be super careful that you are writing those exactly as you see them. Okay. Is the graph a relation, or could I call it a function? Well, again, we could do the vertical line test here. Anytime I do a vertical line, those are kind of sloppy vertical lines. That's really bad, sorry. Let's try that again. Anytime, actually, I can put, no, that's okay. Anytime I do a vertical line, that's a little better. I must have not had enough coffee yet. Okay, it's only gonna hit once, so it does pass the vertical line test. For every x, there is a single y, so yes, it is a function. Okay, the graph is a function. For every value of x, there's a single value of y. Okay, it's not cool to me for you to say because it passes the vertical line test, because you've never defined what the vertical line test is. Tell me you know what a function is in your answer. Okay, okay, so now we're going to take a look at this guy. Again, this spills off the graph, so you can assume that goes on forever that way like that, and this goes on forever that way like that. Okay, so if I'm reading left to right, I can see that x can actually be anything I want it to be, because it's going to go left forever, it's going to go right forever. It's also going down forever and up forever, the way these arrows are going. So actually, y can be anything I want it to be as well. Okay, so for this guy, the domain is x is a member of the reals, and the range is also x is a member of the, or sorry, y is a member of the reals. Okay, is it a function? Absolutely it is. It passes the vertical line test, but our explanation will be for every single value of x, there is a single value for y. Okay, all right. This guy here, now notice the difference here is this does not spill off the page, but it has a distinct start and stop now. So when we're looking for the domain, okay, the domain only, oh, that was really bad, sorry. Let me, actually let me put a straight line there for you. So we start at -3, okay, nothing exists over here, and we end at 5. I did that bad, but we end at 5. So the domain would be -3 to 5. Okay, for the range, our bottom is at what? About -4, and our top is about 4. So we would go -4 to 4 for our range. Okay, so -3 to 5. When we have a start and a stop in set builder notation, we still start with the x, all the values of x such that, that's what that straight line down is. And then we go bottom is less than or equal to middle is, or variable is less than or equal to top. Okay, so this mathematically essentially says x is in between -3 and 5. Okay, but that's how it's written, always with less than signs. Because this is a line, like it's not a series of dots, we still have to conclude that x is a member of the reals as well. Okay, and then the range, similar thing, we end up being -4 to 4 there. Is it a function? Absolutely it is. And again, we know because for every value of x, there's a single value of y. Okay, give me a relation that's not a function. So any sort of picture where it would not pass the vertical line test, okay? So I threw a circle here because if I tried to draw a vertical line here, that would not pass the vertical line test, right? There would be a value for, if I looked at that x value, I have a value for y here and a value for y here, which means it doesn't pass the definition of a function, okay? Okay, and then the last thing we want to talk about in this kind of review lesson is just graphing. There are 3 different ways we talk about graphing. We could have created a graph using the intercepts. So find the x-intercept, find the y-intercept, and then connect those dots. Using a table of values, or in when we started talking about equations of lines, the slope y-intercept form we could use as well. Just as a reminder, the slope y-intercept form was y equals mx plus b, where m was your slope and B is your y-intercept, so where you hit on the y-axis, okay? So what I want to do as the last couple of examples here is we're going to draw two different graphs, and we're just going to use one with slope y-intercept form, and we're going to do one with a table of values, okay? So let's take a look at this guy. This first guy is f of x equals -1/2 x plus 3. And for this guy, because it's a line, I can see that it is in y equals mx plus b form. That's the method I'm going to use to graph, okay? So I see that my m here is -1/2. That's my slope. That will cause me to go from one point, I'll go down 1 and right 2, down 1, right 2, okay? And I know that my y-intercept is 3, so that's where I'll actually start. So I know the y-intercept is at 0, 3, and my slope is -1/2. So I mark a point at 0, 3. From that point, I'm going to go down 1, right 2, and I can put another point there. Down 1, right 2, I can put another point there. Once you see what your dots are doing, get out a straight edge and you can connect those dots. You know that this is a line just from all of your work that you've done in 10C. So grab your ruler, draw that straight line. It would look like that. Okay. Now, the next guy is going to be a little new to you. It's g of x equals x squared. Now, when something's a little new, table of values is the best thing to do because you're going to generate a few points and you can kind of see where the dots go. So to do a table of values, you pick some random values for x. I happen to choose from -2 to 2. And then you're going to take those values and you're going to plug it into the equation. Okay, so what happens when I plug -2 into x squared? Well, that would look like this. -2 is my x, and I'm going to square it. So essentially, I'm asking myself, what's -2 times -2? -2 times -2 is 4. Okay, what's -1 times -1? It's 1. What's 0 times 0? It's 0. You see what I'm doing? 1 times 1 is 1. 2 times 2 is 4. Okay, so now we plot these points. So we plot the point -2, 4. We plot the point -1, 1. We plot the point 0, 0. So go ahead and do that, and then we can compare pictures. Okay, so when we do that, we end up with a picture that looks like that. And that is called a quadratic. The shape is called a parabola. The function is called a quadratic. And this is what we're going to spend really almost a whole month dealing with, just how these work and different parameters that we can do to these, okay? But for now, that's where we're gonna stop. So I have your homework listed. Go through some of these practice questions. The answer key is posted on D2L for you. And if you have any questions, please, please, please make sure you come and check in with me, okay? In the meantime, have a super day. Take care, guys.